prove that f of x equals the absolute value of x, which can also be written in a piecewise way, which I don't know about you, but I find it much easier to compute. So f of x equals x when x is greater than or equal to 0, or minus x when x is less than 0. That is a completely equivalent way of writing f of x equals the absolute value of x. We need to prove that this is continuous but not differentiable at x equals 0, right? So remember, if something is differentiable at a point, in this case x equals 0, then it must be continuous at that point, because to be differentiable, one of the conditions is that you need to be continuous. But it doesn't mean that it's true in the other direction. So if a function is continuous at a point, it's not necessarily differentiable, and we need to have a limit of the limit definition of the derivative needs to exist at the point where x equals 0 in this case. So let's have a look at the absolute value of x. It's a nice function, an interesting function, very common function, widely used, and it looks like this. So it's minus x here, and then it's x here, like that, and it goes off in both directions, right? So we're interested in when x equals 0, right? So if we just look at the function, remember, to be continuous, firstly f of 0 needs to be defined, and it is. So f of 0 equals 0. We know that because we look at the piecewise definition. It says f of x equals x when x is greater than or equal to 0. So when it's 0, it is just 0. So that's fine. So it needs to be defined there. It is. Also, the limit as x approaches this point 0, from both directions, it needs to exist in both directions, and they need to be equal, and they need to be equal to f of 0. So the lim as x approaches 0 from the left hand side of f of x, as you can see, if we're approaching 0 from here, in x, y is also approaching 0 quite clearly. And if we go the other way, the limit as x approaches 0 from the right hand side of f of x, if we approach from the right hand side, we are also quite clearly approaching 0. So the limit, that means that the limit as x approaches 0 of f of x equals 0, which also equals f of 0. So f of x is continuous. Continuous at x equals 0. Right, so now we have shown that this function, the absolute value of x, is continuous when x equals 0. We need to show that it's not differentiable. So what we show there is that the limit of the derivative of the function as x approaches 0, we need to show that that limit doesn't exist. Right, so before you kind of jump into first principles derivative, it really shouldn't be necessary. So it's a very simple function, and we can quite clearly see from this side of the y-axis, when x is negative and approaching 0, you can see all the way along this line the f dashed x is minus 1. From the other side, f dashed x is 1. It's a very, very simple function. So what that is telling us is that as we approach 0 from the left hand side, f dashed x approaches minus 1. So the limit as x approaches 0 from the left hand side of f dashed x, well, that is going towards minus 1. So this is just minus 1, minus 1, minus 1, minus 1. The limit as x approaches 0 from the other side of f dashed x, as in the actual derivative, is 1. So that is showing us that the limit as x approaches 0 from the left hand side of f dashed x does not equal the limit as x approaches 0 from the right hand side of f dashed x. Well, if they're not equal, then this limit cannot exist. So that's telling us that the limit as x approaches 0 of f dash x, the derivative, does not exist. And if the limit doesn't exist, then it's not differentiable. Therefore, f of x equals the absolute value of x is not differentiable. At x equals 0.